So hello everyone, this is Akash and welcome back to yet another video. Today I'm back with another topic, which is square root decomposition. So you might have heard of it or you might not have heard of it. It's an advanced topic. Some people say it's an advanced topic, but we're going to be breaking down every single thing related to square root decomposition. So I hope you'll enjoy this one. And yeah, let's jump right into the video. And just in case if you have if you think this way that these are like the advanced topic and you might not want to learn it, it's completely fine. But I'm gonna be explaining these topics in a very simple terms. So I've kept these teachings or explanations very beginner friendly. So even if you are not even if you don't do competitive programming, I think it's going to be just fine. So in case if you're interested, just stick around till the end. And without further ado, let's begin with square root decomposition. Let's go. Alright guys, so square root decomposition. Let's jump right into what actually is square root decomposition, right? So I've written down a bit of theory over here. It says it allows you to perform some common operations in order of root n. So we have understood till now how to process queries in order of logarithmic of n by using segment trees and merge sort trees, things like that, right? But as the name says, this allows us to perform queries in square root of time, right? So instead of calculating in like logarithmic of time, we calculate by using reducing the problem, the major problem into sub problems of size root n. You can say that, right? So I've written down over here ki we divide the array into square root of n sized blocks. So what does it means is so let's say we have been given an array, right? So we have been given I would have written down that so okay, before seeing this problem, let's see a basic problem, right? So basically we have been given an array, let's say, okay, so an array of size n is given, right? So 1 2 4 2 6 8 7, something like this, right? And like 10. Cool. Now along with the array we have also been given q queries, right? So in each query we have been given L and R, right? And we have been given q such queries. In each query we need to calculate the subarray sum from L to R. Okay, so let's say L was 2, 0 based indexing, so it will go from here, and let's say R was 4, so 2 3 4, right? The sum of this thing will be 8 plus 4 will be 12. Now you can easily do this with prefix sum in order of 1, right? You know that this is a basic concept, right? But in case I tell you you don't have to use prefix sum, and then you have to solve this problem in order of root n for each query, then how would you do this, right? How would you approach it? So the idea behind the square root decomposition is we take the whole array and divide it into square root blocks, right? So here the size of array is 9, right? Just a minute. So let's choose a color. Here it is. Cool. Here the size of this array is 9. So I divide the array into three sized blocks. So 3 3 and 3, right? Now when a query comes, right, let's say a query came where L was 1 and R was 2 3 4 5 7, let's say. Cool. So this is 2, this is 7, right? So we need to find this array, okay, this subarray, I mean, right? So as you know, we can do this by prefix sum, but when we try to do this with the square root decomposition, so we divide the complete array into square root sized blocks, and then we process those blocks instead of elements, right? So instead of going for each I from L to R, we iterate on the blocks, right? So how many blocks does it completely cover? It completely covers just one block, right? So this block will iterate over these blocks, right? And each block is of size root n, right? And how many blocks do we need? How many blocks do we need? That is nothing but n divided by root n, because root n is the size of each block. And we studied this in mathematics, that n can be represented as root n into root n and divided by root n, which is this thing. So the total number of blocks would be root n as well, right? So the size of each block is root n, and the total number of blocks are root n as well. So as we are iterating on the blocks, right? So the complexity for each query reduces down to order of root n. Now how exactly do we do this? First of all, whatever blocks are completely inside this segment, right, we take them separately. So like it would have been there would have been multiple blocks inside this segment. So as I'm saying we are iterating on the blocks. So you can consider that we would be maintaining the blocks sum. So the sum of this block is let's say 2, 6, 8 and 16. So this is 16, this is 20, and this is 7, right? So we are iterating. Let's say this was x, or not x, let's say this was 20. Just take anything. For instance, this was 15, right? Just a minute, yeah. So if these blocks are completely inside, we take them directly. So 20 plus 16 plus 15, which is 51, right? And the blocks which are intersecting with it, which is the first block and the last block, it will only be the first and last blocks in the worst case, right? The first block and the last block can only be the one that are intersecting, right? So there would be 2 such blocks at max which would be intersecting. Other than that, all the middle blocks would be right completely inside the segment, right? So for this thing and for this thing we can take separately. So we can begin from L and go all the way up to the block size or the next starting point minus 1. So the next block was starting from 2, right? So we go from L to the next starting point minus 1. So this thing, and for the right part we go from the ending point of the last second block. So this was maybe this, and we go do that plus 1, and from there we go to R, right? So we begin from here and go all the way up to R, right? So this is how we handle the first and the last block. We're going to be seeing this in very detail. So don't worry if you didn't understood this in the first go. If you have gotten a basic idea, that's good enough for now. Let's proceed. So I've written down another problem over here, right? So we have been given an array and q queries. So in each query we just saw how to do a prefix sum, but instead of prefix sum we need to find the minimum element from L to R in square root of time for each query, right? So this is the same thing, man, same thing. This is, let's say, and even if it was not a perfect square of anything, so let's say this array was not 9, because 9 can easily be decomposed into 3 sized blocks, and 3 sized blocks could be and 3 is a multiple of 9, right? So this is like, this completely fits into the square root decomposition thing. But let's say if our array was 10 instead of 9, so there would be one more element. Let's say this was 5, and so we don't need to worry about anything, because we can just add identity elements. Now identity elements are those elements that do not change our answer. So here we are calculating the minimum element, right? So we can add plus infinity, right? Plus infinity. So this is infinity and plus infinity, because this will not change your answer, right? So the minimum value for this block would be 5, right? And now our query would be there are q queries, and each query we've been given L and R. Okay, so in each query we have been given L and R, and now let's say we have to find the minimum element from here to here, this 5, right? And to do this, as we just saw, we divide this array this into square root sized blocks. Cool. So now we iterate on those blocks. So let's say I divided this array into 3 sized blocks. So first block was this thing. So I am storing the minimum element for each block. The minimum element for the first block is 1, right? This thing. Okay. The minimum element for second block is 6, The minimum element for third block is 2, right? Nice. The minimum element for fourth block is 5, right? Okay, so now we need to find for this segment. So we see first of all what are the segment that lies completely inside this L and R. So there are two segments. So we take these things and take minimum of them, which is 2, right? And now we proceed with the first and the last block, which are intersecting. So we begin from L all the way up to the starting point of the second block minus 1, so which is this thing. And similarly for the last point, last part, we begin from the second last block ending point plus 1 to R, so which is this thing, right? So when taken minimum of all things, this would be minimum of 4, 1, which is these thing. Now the blocks are, the minimum blocks are 6 and 2, so 6 and 2, and the last is 5, so 5, minimum of this thing. So the minimum of this thing would be 1, so 1 would be our answer. And as there are root n blocks of root n size, right, so we are iterating on blocks, so that would give us the complexity of order of root n into q, because there are q queries, and each query we are solving each query in order of root n. So I hope you got it. This is not very hard to understand, right? We're just dividing the complete array into multiple blocks, right? So that is quite easy to do, right? I've written down the implementation over here. Just a minute. Yeah. So how do we do this? This was an array, input array. So okay, and we need to find the size of each block. So what is the size of our block? Which is the square root of n, and we have added 1 just because it is always better to take seal, right? Because the square root of 10 would be integer what? Like when we need to find the integer square root of 10, that would be 3. But since if we take 3 sized blocks and we take root n such, so like 3 into 3 would only have 9 elements, right? But our size was 10, so that's why we take seal of root n. So that's why we're adding plus 1 over here, just to be safe, on the safer side. So this would be our length of each block, and then we saw that root n would be the maximum size. So like or the root n would be the maximum number of blocks that we would need, right? Because root n the number of blocks, and each blocks consist of root n size, so root n into root n gives us n. And just to be safe over here, we have done root n plus 1, and when this is multiplied by root n plus 1, so like root n plus 1 is the size of each block, and root n plus 1 are the total number of blocks, so that gives us with n plus 2 root n plus root n, and this is 1, I guess, yeah, something like this, and root n 1, yeah. So this is obviously greater than n, right? So that is why it will not overflow. This is at least n plus 1 or greater than n plus 1 essentially, but yeah. Okay, so now how are we, this is the code, by the way, for solving the prefix sum problem by square root complexity, right? So how are we exactly doing this? This B array stores the sum for each block. Now I'm starting from the 0 and going all the way up to n, right? Okay, and we're dividing I by len. So len, let's say our array was of size 10, n was size 10, square root n ceiling of that would give us 4, right? So we are dividing our array into 4 sized blocks, and we need 4 such blocks. So something like this, for this thing, and this thing, right? I hope you understand this, right? And now since our array the block size, let's call this m, so m is equals to 4, so the elements of 0 1 2 3 would be in the first block, 4 5 6 7 would be in the second block, 8 9 10 11 would be in the third block, 12 13 14 15th index element would be in the fourth block. So these elements when divided by 4 gives 0, these elements when divided by 4 gives 1 2 3, right? So that is exactly what we are doing over here. So I by len gives us the number of block, right? and then in that block we add AI over here. I hope you get this. This is pretty straightforward, right? Okay. Now we need to calculate the the sum from L to R, right, in square root of n. So I'm doing an L by len and R by len to determine which is my starting block and which is my the last block, right? Because if we need to find the block, the number of block which I'm on, so that is basically, let's say if I start from 9, so ninth element is in which block? That is 9 by the size of each block, which is 4. So I'm on the second block. That is exactly what we are doing, L by len and R by len, which will give us the number of block I am on, number of block that I'm on, right? So if if the starting and end point are on the same block, so let's say from 1 to 3, so then we don't do this thing because there is nothing in between two that is that is completely inside. So we just begin from L and go all the way up to R. This is square root of n, right? Otherwise, if it is not, that's why we have done this condition over here. Otherwise, if it is not, then this thing is, this thing is for the segments that are completely inside this range. So CL is the number of block of for L, right? So let's say I needed to find from 2 to 13, right? So 2 divided by 4 is 0, 13 divided by 4 is 3. So I need to start from the 0th block and go all the way up to 3th block, right? So whatever blocks are present in between, these we can just take directly. So from 1 to second block. So that is exactly what we have done over here. CL plus 1, this was CL and this was CR. So from CL plus 1 all the way up to CR minus 1, take those blocks directly. So we took these blocks directly, and for the first and the last one, which are partially intersecting, so we begin from L and go all the way up to CL plus 1 into len minus 1. So the CL plus 1 into length would give us the starting point for the second block, but since we need to go one lesser than that, that is why we subtract 1 from this. And similarly for the last block, we do CR, which was the last block, into len, so into length, like the length of each block, and then we begin from there and go all the way up to R. I hope you get this, right? This is pretty straightforward. This is just all mathematical stuff, right? I hope this makes sense, complete sense, right? Okay, so I hope you understand this. Just in case if you don't, this is like you can just reverse the part where you dropped off from, and yeah, it will be very obvious to you. And now we're going to be seeing a little trickiest problem, and we're not going to be discussing everything regarding it. We're just going to be discussing the general idea, right? So yeah, let's move on to that problem. Okay, so here's the problem. Just a minute, let me change the color here quick. Cool. Let's do this violet. Okay, cool. All right, so number of pairs after increment. You are given two integer arrays, nums1 and nums2, and a 2D integer array queries. Each query I is of one of the following types. The first type of query is 1xy val. Add val to every element in nums2 from x to y. Cool. The second type of query, in that query we need to compute the number of pairs of j and k such that nums of j plus nums1 of j plus nums2 of k is equals to dot. Return an integer array answer where answer of j is the number of pairs for the jth query of type 2, right? So yeah, this is pretty straightforward. We have been given two arrays, right? So the first, I've also written down the constraints over here. The first array can only be up to size 5. The second array can be up to size 5 into 10 to the power 4. The queries at max could be 5 into 10 to the power 4, right? So essentially in this problem, nums, there are like two arrays. So nums1, it's like let's say 1 2 3, and we've been also given this second type, the second array, which is like 1 4, let's say, and it's gonna be, let's say 3 and 10. Just taking a random sample over here, right? And let's say the query comes, so the query is given as second type of query it is, and it is 5, right? So it this the first thing denotes this is the first type of query, the second type of query, my bad. So this is the second type of query, right? And this is the target, right? So we need to find the number of pairs, I in nums1 and j in nums2, such that nums1 of I, so let's say I, just a minute, this is I and this is j, let's say. So this is like nums1 of I plus nums2 of j is equals to, and this is the query, this is queries of 1, which is, let's call this target. Just a minute, what is this happening, bro? Cool. So this is equals to target, right? And the target was 5, so there are 2 such pairs, 1 and 4 and 2 and 3, right? So for this we'll return 2 because there are 2 such pairs. Cool. Now the catch is the catch obviously is key. We need to add we also need to add elements, right? So the first type of query can also be given where we have been given 1, L, R and the val, right? So this indicates this is the first type of query, and from L to R, which is this thing, just a minute. So from L to R we need to add val to all the elements in nums2. So nums2 was the greater the bigger array, and for each element from L to R we need to add the val to the elements, right? And now after that, if a query comes of type 2, then again we need to calculate the number of pairs, right? So the number of pairs will not remain constant. So if there were 2 pairs in the in this query, then it is not guaranteed that there will be 2 pairs after this query, right? So how would we do this? Now you might think of a brute force approach, right? If we have been given this second type of query, then just iterate from L to R and add val to all the elements, right? So if this was my array, so this is, let's say, L, this is R. So the brute force approach could be begin from L, so and go all the way up to R. This is nums2, and add plus val over here into this sub array. And when a type 1 query comes, right, so then you calculate all the pairs, as this is like only up to the length of this is only 5, and the length of this thing is 5 into 10 to the power 4. So the complexity becomes n into m, which is like 25 into 10 to the power 4, right? So this is 2.5 into 10 to the power 5, which is great. This is not that much, so the n into m approach would work, the brute force would work. But the only problem is we need to also add the values in nums2, right? And nums2 is a bigger array, so just in case if our L is 1 and R is n, so this is like order of n operation, and our queries are 5 into 10 to the power 4. So in the worst case, the brute force operation could be all the way up to order of n, and for each query this would be order just a minute, this would be order of n into q, which is not very optimal. And yeah, so this would be 25 into 10 to the power 8, which is 2.5 10 to the power 9, which is much greater than what we want, right? So this will not be accepted, and yeah, so this approach will not work. So how to do this problem? Similarly, we can just do this problem via using what we just discussed, by using square root decomposition. So the general idea to solve this problem is we divide this array, the second array nums2, into square root sized blocks, right? So let's say this was my the second array, right? nums2 array. This is 3, 6, 9. I'm just taking a completely which has a complete root, right? So I've taken a nums2 of size 9. So 3 into 3 is 9, which is like a complete square, right? Oh, okay. So this is nums2. Cool. Right. So now we divide the second array into into square root sized blocks, so which is 3. This is the first block, this is the second block, this is the third block. And since nums1 can only be up to 5, right? So we don't actually need to care about it. This is just 5, right? So 5 is just a constant, it wouldn't matter. We don't need to do anything for this. Cool, right? Okay, so now we divide the second array into root and sized blocks. So we have divided the second array in root and sized blocks. So I'm just calling that m. So m is equals to root n over here and ceiling of this thing. Okay, so m over here is 3. So we have divided our array into 3 sized blocks, and there are 3 such blocks. Cool. Okay, so now for each block we also need a map, right? So this is like we'll create a map for the first block, we'll create the map for the second block, we'll create a map for the third block. How exactly we would do this? We'll create a array of maps, right? So m is the number of is the size of each block, and when you divide n by m, so this will give us the total number of blocks. You can directly take m also, this is fine, because root n into root n is n, right? Or you can do an n by m or seal to this, right? So this will give us the total number of blocks that would be needed, right? So sz equals to, this is the size of my the number of maps that we would need, right? Or the total number of blocks that we have. So that is n divided by m. So m is the size of each block and n is the complete size of array. So how many blocks would be there? N by m, right? Basic mathematics. Okay, so we need to create an array of maps of size sz, right? This makes sense, right? Okay, so now for each element we iterate just like what we did over here, right? This thing. So now for each element we iterate, and we know which map it belongs to, right? This is the first map, this is the second map, this is the third map, right? So for each element we just know which block does it belongs to. So let's say 1 2 1 was here, so in this map 1 occurs 2 times. We're creating frequency map in, essentially. So 2 occurs 1 time, and this was like 3 4 6. 3 occurs 1 time, 4 occurs 1 time, 6 occurs 1 time. This is like 8. So 8 occurs 3 times over there. So we have created 3 maps, or the number of the number of blocks would be the number of maps that we would need, right? Okay, this makes sense. Cool, right? So now if we need to process a add query, so the first type of query, so now this type of query, right? So you would have gotten the idea. We will not add this value to all the elements. Instead we'll create, just like we created a map array, we'll also create a lazy array. If you would have studied the lazy segmentary, this is exactly the same thing. We are also creating a lazy array. So this was like the maps array, and like we're also creating a lazy array. So lazy array would mean कि let's say I need to, this is my L, so L is my 1 2 3 4 5 6 7, and R is 7. So I need to go from here, let me use a different color. So I need to go from this thing and go all the way up to here, and we need to add plus 10 over here. So we'll not add this to all the elements, right? Because that is order of n, which is much greater, which is, spoils our time complexity. So we'll not do that for every element. Instead we'll do that for all the blocks, just like what we discussed right now. So we're iterating on the blocks that lie completely inside. So this lies completely inside. So that is why we have another array called lazy. So as we need to add plus 10 to this, so for this block we'll add plus 10. So this is like the lazy array. So we'll add 10 to this lazy array. And since the first block and the last block are the partially intersecting one, they could be completely intersecting also, right? If a query comes from 1 to n, that is completely fine. But I'm treating the first and the last block as partially intersecting because that makes our case easier. So for the first and the last last part, we do not add that to the lazy thing, because the lazy denotes the complete value added to the block, right? But the first and the last block may be partially overlapping, right? So that is why we make this, we change the elements directly. So 2 becomes 12, 1 becomes 11, 8 becomes 18, and this 8 also becomes 18. So in the runtime we're changing the frequency map, right? So instead of 2 being occurring one time, so we decrease this frequency, we remove this from map, and we insert a 12 over here. Similarly, 18, we don't this 8 was occurring 3 times, but 2 8s are deleted, so this will only occur once, and 2 18s are occurring, so 18 is occurring twice. So in the runtime we are changing the map continuously as our update query comes, right? So that is why exactly why we created an array of maps, right? And the lazy value of the middle block is updated with 10. That indicates that this blocks, all the elements of this blocks have 10 added to this thing. So this is not 3, this is 13. This is not 4, this is 14. And similarly, this is not 6, but this is 16. Or in other words, this is not the element x itself. This is x plus lazy of this thing, lazy of this block, right? Block of x. That is what I'm talking about. So I hope you got this. So now we know how to process the first type of query. Now how to process the second type of query, that is calculate the number of pairs of nums1 of I plus nums2 of j is equals to target. Okay, so as you know, we can iterate on the nums1 because nums1 is only up to 5, right? So we can iterate on all the values of nums1, so that doesn't make much sense, right? So we're iterating on all the values of nums1. So nums1 is fixed. Okay, nums1 is fixed. Cool. So now nums j is equals to target minus nums1 of I, right? Okay, but nums1 was fine because we didn't do anything in nums1. Every jargon that we did, the square root decomposition, the array of maps, the array of lazy, we did this for nums of 2 because that was the larger array, right? So this thing will remain as it is. But when you see this nums, this is not nums, this is nums2, right? Nums2. Okay, so this nums2 is not nums2 itself because it has a lazy value as well. So nums2 has lazy added in this, right? A lazy value added in this, lazy of block of j. So whichever block this j was on, that value has to be added in this nums2, right? That is why we created this lazy value, right? Okay, so this nums2 of j is not nums2 of j alone. This has a lazy value added to it. So this 3 is not 3, but it has a lazy value added, which is 10. So that is why exactly we are doing nums2 of j plus lazy of block of j. As this is now equals to target and minus nums1 of I. Okay, this is good. We're getting there. Almost we have gotten there. Okay, so now nums2 of j is equals to target minus nums1 of I minus lazy of block of j, so whichever block this j was on. So this is our expression finally, and we'll count such pairs. So my nums1 of I is fixed. We can iterate on all the blocks as well in root n. So this we can fix this also. So this is order of 5 to process each element of nums1. 5 into, we're iterating on all the lazy blocks, so this is root n. Cool. And we're counting all such pairs. So target minus these values and these values, right? So let's say I'm iterating on this block. Right? So I decrement. I would have already fixed our nums1 of I before this, and I'm iterating on all the values on nums of I, right? So I would have a value of nums of I decrement that from target, and I decrement the lazy value from here, right? So okay, this becomes my nums2 of j, and I count how many these values are present in this value by using that frequency map, right? That is exactly what we do. That is exactly what we do. So just in case if this expression would have resulted into 18, then we would have added 18 to our count. We would have printed 2 over here because there are 2 occurrences of 18. I hope you get this. I genuinely hope you get this, right? Okay, so in the end our problem boils down to this particular expression. right? And that is exactly it. The problem is actually solved. We're iterating on all the blocks, man, all the blocks. We're fixing nums of I, this is order of 5, and we're iterating on all the blocks. So whatever the lazy value of this block is, lazy of 0, we decrement that from target, we decrement the value of nums1 of I, and we see that how many values of this expression are present in this block. Then similarly we move on to this block, we decrement the lazy value of 1 from the first block, we decrement whatever we choose in nums1 of I to be, and we see how many values are present in the second block. Similarly we do this for all the blocks, and by using this logic we store our answer in count, and in the end we just add this answer to our array, and we return the array, right? That is exactly how we'll solve this problem. That is it, this is done. So I hope you get this. I genuinely hope you got this problem, and just in case if you didn't, you can watch it again and you can understand the concept more clearly if you want. I'll link down the CP algorithms blog in the description. I'll link some practice problems also. Along with that, you can go to LeetCode and check out the editorial, or the official editorial, or the solution section, just in case if you want to understand this thoroughly, or like if you want to see the code for this. And yeah, so we are done for today. I generally hope you got this thing, square root decomposition, and this is like another tool in your box that is added now. So I hope you enjoy this. I hope you enjoyed learning this, and I'll see you guys in the next one, damn sure. So yeah, bye bye, take care, and as always, Radhe Radhe.